Good day. This is the video for 9D chemistry, and it's May 20th. And if you're seeing this, you probably missed the video, so just watch this and then write me afterwards an email. Let me know that you saw it and took some notes. Good. I'll wait for some folks to come online here, and we'll take attendance here on May 20th. So I got a couple already. Wonderful. Thank you, Macy and Aaron. Whoa, and I got three more. Good morning, Rhea, Victoria, and Lena. Freedy, good morning. Natasha, good morning. Sam, good morning. Very good. Well, oh, and there's Lars too. Let's put up a little review diagram to remind us of some stuff, and then we'll start up with some new things once we get everybody here. So here's a diagram, and that's potential energy. And here we can say reaction stages. Okay, so and there's Raphael. Good. Good morning. The stuff we start out with in chemistry. So the first line I draw, this is where the what are. The what are. What are the things I start with in chemistry before the reaction? Just type in, and I know we're up and thinking today. What do I start with? This would be the little line for the what. Okay, I'll wait for a couple responses. And a couple already good. Thanks, Rhea and Lena. They're correct. It's the reactants, the things you start with in chemistry. Good. So let's say my diagram looks like this. And you guessed it. What's the line for here? The stuff I end with, the stuff I end up with in chemistry. It's called the what. And while I'm doing that, I'll take roll. I see Isabel is here. Any others here that haven't said hello, please say hello. And I got it from Aaron, from Lena, and from Macy. It is indeed the products. Okay, now we're getting warmed up. This is good. And I got 12 of you. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Still got somebody that hasn't said hello, but I got everybody that's listed. Okay, let's just keep going. So is this an endo or exothermic diagram, this potential energy diagram? Endo or exothermic? So warming up. Check your notes from last week. If you're not sure, I'll tilt the board. No, that doesn't help. And several have it. Good, including Victoria and Natasha and others. It is indeed endothermic because we have to put in energy. From here to here is called the energy. What's this line called? From here, the reactants up to the top of this hill. The energy. Check your notes from last week if you were here. And several folks have it, Isabel and Rhea and Aaron. It is indeed the activation energy. Okay, great. Good. We're getting our gears going. That's wonderful. Okay, what's going on with the chemicals right up at the top? What sort of state are they in, and what has happened to them at the very top of this diagram? What's happened to the reactants right up here? What have they done compared to where they started? So you may have to type a few words for that. I don't want just what they're called, Aaron, but I want what's happened to them up here. Physically, what's happened to the chemicals, the reactants, when I get to this spot up there? Good. Now I get some more involved answers from people. Natasha, that's a good way to say it. Yep. Rhea and others. Yeah. The bonds have been broken. So remember, chemistry is about breaking bonds and then making new ones. So here the bonds have all been broken, totally broken up. And it is indeed called the activated complex. So the bonds are all broken up at this point. And then in this case, we make some products. Okay, I got an open-ended question. Okay. Yes, exactly, Aaron. Right. The open-ended question is, can you think of any endothermic reactions or processes where this would be happening? In other words, what sort of reaction could this represent that would be endothermic? So look back at your notes or just think of something. What's something where it's endothermic? What could this diagram could represent what reaction? Ooh, that's a cool one from Aaron, photosynthesis. So it could be a diagram for photosynthesis. That takes energy. Takes the sun, doesn't it? Good. Anything else? Oxidizing something. Good question, Natasha. Sometimes oxidizing is endothermic and sometimes it's exothermic. So it kind of depends. Like if it's rust, it's actually exothermic. If it's oxidizing gold, that would be really hard. That would be endothermic. How about something you do in the kitchen where you got to apply heat, where it's endothermic? Anything you do in the kitchen that would qualify for this sort of diagram? What could I do in the kitchen that would represent this sort of circumstances? Yeah, I love it. Yeah, heat something. Could we be a little more specific? Make coffee? Yeah, probably. How about boil water? All right, Isabel, that sounds good. Okay, I'm cheating a little bit here. Boiling water, it's not a chemical reaction, but it is a process that requires energy. And as you'll find out next year, we're not breaking apart the water molecules themselves. We're breaking one water molecule from the next one and then making them into a gas. Okay, so I'm cheating a little bit. Rhea is a good one too, cooking food. So if I'm cooking food, that is a chemical change. So if let's say I like cook beans and make them soft, that's a chemical change. And a lot of other foods are too. Okay. And there's Ava. Welcome, Ava. Thank you for checking in. Anybody else out there, let me know you're there. Yeah. Okay, good. All right. When last we met, we began a new type of diagram, and I want to review that and continue with it today. So this is potential energy diagrams. Unless you have any questions, I think we've covered that pretty well, and by the sound of my review with you, you're doing pretty good with it. So I'm going to erase that, unless I can see any quick questions, but I don't. Let's do that. Good. And we started this last week, and it's called kinetic energy diagrams. And I'm going to put one of those up here and just ask you, I know we began it, but let's make sure we remember what this is about, because we're going to use them more today, okay? So let's check it out. So for this, it's sort of like different because the energy is down here. So this is called the kinetic energy of the chemicals, of the particles. And I bet that's right in the blur. I bet you can't see that. So kinetic energy of the particles. And over here is the number of particles or molecules. Okay, good. Kinetic energy. Let's put this as no numbers. We're just going to say low and high. High. Okay. If molecules have a lot of kinetic energy, can you describe them so we know what we're talking about? Molecules or particles. They got a lot of kinetic energy. What's going on with them? What does a lot of kinetic energy mean? So I got some particles. They have a lot of kinetic energy. What does that mean? Type in a few words for me. Good. Now I'm getting some feedback. Thank you for participating. Here we go. So they're moving fast. Yeah, Natasha. There's movement. They have a lot of movement. Yeah. Okay. So now we're talking a lot of movement. Now, so they're moving exactly. Now, they don't all have the same movement. In other words, they may hit each other. One may go slow, the other may go really fast for a second. So they're varying. But in general, folks, the higher the kinetic energy, the more molecules are going faster. Okay? Right. If I have a low amount of kinetic energy, you can imagine they're moving slower. They're probably hitting each other more gently, maybe not as often. Maybe some are faster, but a lot of them are really pretty slow. So what we're going to say is, let's just take some molecules, some particles at like your basic temperature, okay? And remember, this is the number of particles. So let's say I got a few slow ones at whatever temperature I pick, maybe like room temperature. And I got a lot that are in the middle. And I got a few fast ones over here, okay? So they have high kinetic energy. So that could be what's called my distribution of molecules. And there's Carlotta. Thank you for checking in. So that's the science name for this, distribution of molecules. Oh, well, particles, but it doesn't matter. I can use those two words interchangeably here. Molecules and particles both work fine here. Okay, so distribution of molecules. Good. Let's say I put an imaginary line here in this diagram. And let's say this line is the amount of energy those particles need, the amount of kinetic energy to be able to hit and break apart, okay? Well, essentially then, what's that energy called? That imaginary line would represent the energy that we talked about in the other diagram. So what is that imaginary line representing for molecules? Again, they're going to hit and then they could react. So that line could represent the energy. One person's got it. Let's see if some others respond. Think of the other diagram. I know it's in a different place, but all right, good. Rhea and Natasha got it. It is indeed the activation energy once again. So in this diagram, I'll abbreviate energy to EN. In this diagram, it's like a line, and the ones that get past that line get to react. Like these suckers out here, they can all react, right? Because they've got more than enough kinetic energy to react. So I'm going to put I'm going to give us a little striping and say, hey, these puppies can react, okay? Huge. I think that's all review. Can I ask you, those that were here last week, is that about as far as we got last week? Can you let me know? Yes, yes, or no, no, we had more, Mr. Weiss. And in the meantime, I got one or two others that haven't said hello. There's one right there. So good morning, Ada. So it's about everything we covered. Victoria says yes. Thank you, Victoria. Good. Then I'm going to take this down. I'll erase it later, unless you guys, I think you can see that all right. Unless you guys have any question. Good. I got yes, yes from lots of you. Good. Let's take that down. And now let's start with a new board. Okay. Okay. Can you see that? Yes, you can. I'm going to start out with a similar diagram. Why? Because I need a new one so it's not quite so messy as the last one. So let's start out again, and we'll just do it like this. Let me make it bigger. So a number of particles and kinetic energy. And that's enough, I think, because we just drew the same diagram, okay? All right, let's draw the same first scenario. So here's our starting distribution. We had something like that, okay? Okay, let's say we heat these molecules up. Extend that line a bit. If I heat these particles up, what's going to happen to my bump? If I heat these particles up, what happens to the bump that represents the distribution? Right? So now I put them under a stove or something. What's this gonna do? What's that bump gonna do? I heat up the particles. So I'll wait for a couple responses from you folks. How will the diagram look different when I heat up these particles? Hint, this is low kinetic energy. This is high out this way. What's going to happen with this bump? Okay, now I'm getting some guesses here. That's what I want. I got moved to the right, I got get taller, and I got get bigger. Okay, so bigger or taller would mean in this case that I've put in more particles. So I'm not putting in more particles. I'm just heating the ones up that I've got. So let's talk about what Natasha said. She said the bump would move towards the right. Aha, if it moved towards the right, then I've got more particles that have a higher kinetic energy. And that's the right answer. Ha ha ha. So here we go. I'm going to draw this one then at this temperature. So let's say the green is at a room temp, T for temp. Let's say the red is at a hot temp. And let's say we do that now. Okay, so let's see if I got anybody else coming on. Nope, I've got everybody here that's going to be here. Here we go. So I've got less of them at a low temperature. Now, I've still probably got a few that are kind of, once in a while, even if they're going faster, somebody gets hit and somebody's going slow for a second, okay, before they get hit again. So just as a snapshot, I've still always got a few that are down here. But now my bump, I probably got more that are warmer and less that are cooler. So my bump has shifted to the right. And I hope that makes sense to you. So that's a hotter temperature. Okay, I'm not going to write anything else on that for a second. Now, if you're really thinking, you might notice that I put that bump a little bit lower. It is. I'll let you mathy type people think of why that is. And before we answer that, I think this will then make the answer easier. Let's go to our starting temperature again. And now I'm going to do a third one that is going to be a colder temperature. So the starting one was green, and I'm going to do the next one in blue. What's going to happen to the bump when it gets colder? What's going to happen to this bump as I make the particles, same box, as I make them colder? And Isabel, it's a good question. We're going to answer it in a second. Yeah, they move to the left. Good. Let's see if anyone else adds something to that. There's something else as well. What happens to the bump? The bump moves to the left and the bump gets higher. Let's have a look. That's the cool temperature, or cold. So I'll write here cold. And the one that's moved to the right, I'll write hot. Okay. Yeah, why? Why is it getting higher? Can someone explain in words why that sucker's got to be higher now at a lower temperature? It's a bit of a math thing, but there's several ways to describe it. Why is the cold temperature one higher? So I'll write here cold temperature in parentheses, bump is higher because, and let's see if we can get any good answers. Because why? All right, so let's see if we got some good guesses out there. I'm going to read some guesses. Oh, I got a lot of good guesses. Okay, so Aaron says less particles are hot, and the height of the hot particles is now added to the cold particles. Yes, Aaron, you're getting warmer, or colder in this case. Yeah, that's getting towards the idea. Let's see if others can add to it. Natasha adds, all the particles are squished on the left side of the chart. Yes, and we're going to see why that is, Natasha. In a sense, they are squished on the left side of the chart. Let's see what Ray adds. The total number of particles but smaller distance to cover. Yeah, it's not really distance. Okay, it has to do with this, okay? Let's say I make a graph. So forget this for a second. I make a graph of all the heights of all the students at the Kennedy School from Vorschule to 12th grade. Are we in agreement that there's going to be a lot of different heights, right? And they'll be all spread out, okay? Now, let's say I take the same number of students, but I take another population that has them all in the first grade. How will the number of heights be different? Well, same number of students, same number of particles, okay, same number of students, but now it's all going to be shifted to just a few values. and that those values, those values in mathematics are called the range. So let's go back to particles, okay? If I've got the hot particles, the red ones here, well, if I heat them up, I've got a lot of different kinetic energies they can have. Some can be slow, some can be fast. But as I cool them down, there's less possible different kinetic energies that you can have. Why? Because at a certain point, I can't go below zero. So that's really it. So I get less of them, even though the same number of particles are there. So ideally, if I was doing this very mathematical, and this will be a science you'll study in the next couple of years, or math called calculus, the area under each curve, if I could measure the area, and I know that's not easy for you now, should be the same. So I might have overdone a little with the blue, I don't know. But what happens is there's a lower range of values. So because I shoved them all this way, some of you who intuitively had that feel were right. So there's less values possible. So we say the range of values is less. So the number of particles having those values is got to be more. Okay, so bump is higher because range of possible kinetic energy values is now much less. It's the same number of particles, but the range is less. The possible numbers of the values for their kinetic energy. That comes from a science called statistics, or a math called statistics. So if you take that, sometime you may have a little more to do there. I see I got another person. Anybody else hasn't said hello yet? Just to kind of recap, I've got Natasha, I got Ava, I've got Isabel, I've got Aaron and Raphael, I've got Anna, Freedy, I got Macy, Lars, Lena, I got Carlotta, Rhea, Victoria, and Sam. Anybody else out there, please give us a hello. Good. Questions from you so far? Okay, so we're going to add now another line. Yes, I know it's rather a busy diagram. And I'm going to add the line right here. And we're going to say this is the activation energy again, all right? We know that line from the last diagram. Remember that? Activation energy. And I'm going to tip that a bit so you can make sure you can see it. I guess you can. So, although my writing's pretty sloppy here. A for activation energy. So this line again. So here's what this means, okay? If I heat up particles, even a little bit, it really matters. More than any other thing you can do, heating stuff up is really important in chemistry. Let's have a look. So if I have the normal temperature, the green one, I've got these particles that can react, right? But if I heat it up, and the shift hasn't been that extreme, but if I heat it up, suddenly I've got a huge number of particles that can react. So in addition to these, I've also got all of these guys that can now react as well. Now, for this diagram, it's all about the area. So look at this. There's a little area, and look at how many times bigger this area is. I don't know, 5, 10? I mean, this is a big increase. So my point is, if I increase the temperature, it really increases the number of particles that have enough energy, right, to hit and react effectively to make the reaction happen. Even a little bit can matter. Okay, I'm going to go back to my first diagram a bit. Okay, first I want to pause here and see if there's any questions. I also want to give you time to make sure you had a chance to write them down. I knew that would happen. Nothing like a good basement. Okay, so if I got that, if there's not any questions, I'm going to write something on the first diagram. We got two. Yeah. Okay, here we go. Okay, so for this diagram, I want to leave this. You can go back to this one in your notes if you want. So I got the activation energy. I just got one line. Well, I'm going to say, what if I increase? I'm going to put a little line off on the right here and say, increase temperature in degrees Celsius by 10 degrees C. Would we agree that's not a really huge change? Okay. It's warmer, but it's not like out of this world warmer. Remember, the lowest temperature possible, you might have learned in physics, is negative 273. There's no highest possible temperature. We can go as high as we want. Well, not forever, but for quite a while. But a 10 degree is not a huge change. But let's see what that does. Now, I know I don't have any numbers here, but let's just sort of estimate what could happen. Okay, so maybe I got a few lower here, not much. And now I'm going to go lower here. I bump. So notice just a little change in temperature. There's the lower temperature. I made my bump a little lower. And I've extended it to the right. Just a tiny increase in temperature really increases the number of particles that are now beyond this line, this activation energy line. So my point is, we can read that, okay. Hey, even a small increase in temperature really increases the reaction rate. The reaction rate. All right, so that's some of that might be hard to read. Let's tip it so you can see it, and I'll try not to make the whiteboard fall over. So I wrote, hey, even a small increase in temperature really increases the reaction rate. So we prove that up here. We have a much greater area, okay? Much greater area beyond the activation energy. Okay. And I'm going to again pause here with questions. I know my diagram's gotten pretty busy, but I may do one more thing with it because it's just such a cool thing. These diagrams, by the way, are really the way lots and lots of chemists and physicists think about reactions and so on, okay? All right, so, okay, good. I got a last question for you about this diagram, and then we're going to talk about this a little bit more in terms of applications. And my question to you is, what would change with this diagram if I added a catalyst? You and I talked about catalysts for chemicals that speed up chemical reactions, right? But they're not themselves used up in the process. So what would change about this diagram when I add a catalyst? What do you think? Type in some guesses, okay? So what would change? Let's just start with the blue line and the activation energy, and what would change if I add a catalyst to this diagram? Look back in your notes and see what a catalyst does for you, how it changes the reaction rate. So if I add a catalyst, and I've got a couple guesses so far, let's see if I get some more. Oh, yeah, good. I like it. Lots of guesses. So here we go. I've got activation energy would move to the left. The bump would be lower. Energy like the energy needed. Don't quite get that. Activation energy, we refer to the left. Activation energy, yeah, okay, good. I got several of you got it. Yeah. So instead of the activation energy here, well, I would need less activation energy. So suddenly I would have, let's make it, oh, don't want it blue. I'll make it black. So I'll say this line could be, I'll kind of dash it. And I'll put here another little star. And I'll say, this would be the activation energy needed if a catalyst were added. Now, I'm not going to shade this again because our diagram's gotten so messy, but can you just imagine it? Look at how much that catalyst changes stuff. Suddenly, things that are hitting with less kinetic energy have enough to break stuff. So all these guys beyond that line can now react. So a catalyst can really, really change things. Yeah, good. A lot of you had that correct. You're doing good. If there's not any questions, I'm going to erase the other board and I want to talk about some applications of this. Okay, Mr. Weiss, these diagrams are okay, but so what? What do I care? Okay, I want to show you why you should care. Applications means where do I find it in real life? Questions about any of it while I make this second whiteboard claim? Okay, can everybody read enough of that? I hope I'm not covering it up, and I hope you see enough before I move it. We okay? All right, and this over here at the left says activation energy needed if a catalyst were added. That's that dashed line with that's in black with the little star. Okay, yeah, okay, good. All right, so what? What do I care? Okay, let's do some examples. You as a person, you as a student. Oh, I got a question. Hold on. Let's get the question answered first from Natasha. If you add more of the catalyst, does the activation energy move even further left? Good question. If I add more of the catalyst, Natasha, at a certain point, it doesn't matter. The catalyst is something that allows the other molecules to find an easier way to react. And you need a certain amount of catalyst, Natasha, but generally once I have, it's often a surprisingly small amount. And if I add more, it doesn't really help much. It's sort of like the question, it's either there or it's not there. Like when we talked about the catalytic converter, your exhaust pipe and the platinum coated catalytic converter grid. Long as it's there, it doesn't matter. I can add a second one, it's not really going to matter. Okay. So I don't think it matters as long as you have a relatively small amount of catalyst. That's at least my experience with chemicals. I may not be perfectly right, but I think that's generally the way it is, Natasha. It's a good question. Hope I'm right. I've certainly been wrong enough in my life. Here we go. Okay, so let's go to an example. So what? I'll say this is applications. How can I use this idea in my life? You get sick and get a fever. You get sick and get a fever. Why do you suppose people get fevers? This is your body. Your body's making you warmer. Not a lot, okay? When I get a fever, maybe I go up in Celsius a degree or two, not a lot, but your body does this on purpose. Why do you get a fever sometimes when you're sick? Why is your body doing this? What good is a fever? It doesn't feel nice. Why does your body do this? Good. Carlotta's starting soft. Your body's trying to kill the bad stuff. Good. Someone else continue. Your body's trying to kill the bad stuff. So, why a fever? What have you learned here in chemistry? Natasha, so that it can be uninhabitable to the bacteria. That may be true as well. Rhea's on the right track. Killing the bacteria. Could we make a little more? You're getting closer, everybody. Yeah, yeah. Think of killing the bacteria as a chemical process. Here's your white cells. They come up and they want to kill that bacteria. Why do I want it warmer in your body? So it's a process. It's a set of reactions to kill bacteria in your body. Why do I want it warmer? So killing the bacteria is essentially one or more probably reactions. Do we have some things coming? All right, I'll write some stuff to get you going. So you get sick and get a fever. Killing, let's say it's bacteria, involves reactions in the body. All right. Therefore, why do you want a fever? Killing bacteria involves reactions in the body. Why do you want a fever? You may not want it, but why is a fever helpful? A fever is a higher temperature. Why is that helpful? Yain, fill out the idea. The reactions, Natasha, are already starting. They're already there. We're already fighting the bacteria. But why do I want to have it happen at a higher temperature? What about the activation energy? What about the situation? Somebody else jump in. I'd like to get some more feedback from somebody. Why do I want it to be hotter in your body? So it's the possible of values is less. I don't quite understand what you're saying, Victoria. If you can explain that a little more. It's hotter. What's happening to the amount of bacteria getting killed? It's hotter. What's happening to the amount of reactions to kill bacteria? More molecules react. Okay, so a fever means more reactions to kill bacteria happen faster. Remember, it's about reaction rate. Do you want to kill bacteria faster? Yeah, I don't want to be well. I don't want to be sick. So a fever means more reactions to kill bacteria faster. So it's more effective, more bacteria killed. Exactly, Rhea. Now we got it. Now, I'm not a doctor, and I'm simplifying things a bit for you. I can have a really high fever sometimes, and that starts to hurt your internal organs. So there are some things that are not good about fevers, but the general idea is sometimes a fever is not bad. You know, they say sometimes, oh, you want to fight a fever, but actually sometimes a fever can be good because it's the sign that your body is trying to create an environment where the reactions to kill the bacteria are happening faster. Good. We're about out of time. I'm going to leave you with one question, which will be our next example next time. And the example says you have to store nitroglycerin. So, dot, 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 dot. I'll let you think about that for next time. Okay, thanks everybody for coming. We're going to start with nitroglycerin next time. And have a good long weekend, whatever you're doing. Bye.